Organisers for putting on such a good show this week. It's been a blast, I must say. Really enjoyed this meeting. Let me see, where is the control? So I'm going to talk to you about something. Oops, where did it go? That's it. So I'm going to talk to you about one of my favourite subjects, which is catastrophic failure in porous media. And I'm going to look at the sound, that is the noise that these events make when they're occurring, and the vision. Now we have the vision. We can see inside the sample using computer tomography X-rays. And we can put the two together to see whether our previous kind of inferences made from seismology. You know, early in my career, and we saw some examples of this yesterday, we used to draw little pictures of things that might be happening. Distributed deformation before failure, and then localization like this, and then eventually the fault goes through the system, and you get a catastrophic failure, meaning the whole thing breaks on the system size. So to investigate this, you need a lot of people, and sorry, I wasn't finished. So there's you need to build the rig. You need people to invert the data, to do the image analysis, to do this is particle tracking for the strain field, and you need the people to look at the seismic records. You need people to look at the CT images. You need people to understand how to do an experiment in a synchrotron. And so it's a big, every one of these names has contributed to this sort of presentation today. So this is what we're doing. We're directly imaging the damage using a new cell. It's called Mjolnir. Can anybody tell me what Mjolnir is? Who does Dungeons and Dragons? It's Thor's hammer. Okay, I don't know why, but it's called Thor's hammer. And this is it in practice. So we had to design the rig, or Ian Butler, and then make it. And then we run the experiments using this stepped approach with these hold times for the stress. And that is so that the sample in the rig can rotate maybe over tens of seconds to a couple of minutes. So we can quickly scan the image while it's under static load. Even then it will be relaxing slightly, but we still have enough, it's a short enough time to allow the image to be captured. Put it in a synchrotron. This is at the Soleil synchrotron, this first example I'm going to show you in Paris. And we put in a pristine microgranite, something with no cracks in it to start with. And also a version of this rock which had been thermally treated to put in disorder deliberately by thermal cracking. We're not interested in thermal cracking, we're just interested in putting in a material with a higher porosity and a greater compliance to see what difference that makes. And then we can observe the damage. In this case, these are sort of near vertical tensile cracks that happen in the granite. And here are the images that you can get. On the left is the 3D image, and on the right is the 2D section. And one of the biggest jobs that you've got is to isolate or segment the image and look for the things that you're interested in. In this case, it's the microcracks. Okay? So you can have a 3D image like this. You can see there's a lot of vertically aligned tensile microcracks. Initially, they start out randomly distributed in the medium, then they localize spontaneously on this incipient fault plane. And then you can take a 2D section through this, and you can see the difference that the 3D approach gives you. The 2D sections do not capture exactly this pattern. It's really a self-organized process in 3 dimensions that produces the fault. And then you've got these segmented cracks, so how do you characterize them? And what we've done is we've taken a best fit ellipsoid through these fractal objects, And the reason for that is that we can then extract parameters consistently for the crack population. Once we've got the best fit ellipse, we can get the centroid, the location of the crack, we can get the length, the width, and the volume, and then do statistics on those parameters. And we can also get the angle of slope. All of that you get from the best fit ellipse. And then we can get the aspect ratio. A lot of you mentioned that this week and how it might affect seismic observations. We take the crack length to be the length of the major axis, and the intercrack spacing is then the distance between the centroids. And here's some observations. For the untreated sample, I don't know, I've got a pointer. You can see the stress strain history is quite different when you have the heat-treated sample. It's much more compliant after yield because of the pre-existing microcracks we put in, and then it breaks near the peak stress. And the same for the untreated sample. It takes longer to break it at the same strain, at the same strain rate. And what we see is that the porosity increases with this inverse power law. And then bang, it goes bang at the failure time. So that would be a hard failure time to predict from these data. There's no obvious singularity, because we're still dealing with relatively low porosity materials. And it turns out that it's very hard to predict the onset of sudden catastrophic failure in these systems. Okay. And then when we look at the statistics of the cracks, this is the untreated sample. This is the heat-treated sample. And we look at the size distribution by volume. It starts off exponential. That means the cracks are dominated by nucleation. And then it goes to a pure power law, the Pareto. And then it starts to show this bump. Didier Sornet calls these dragon kings. They're not scale invariant. They are characteristic events which are too big for the fractal kind of model to hold. And this occurs in the sample with virtually no small-scale microcrack disorder. So if you've got a very uniform system, you can have really big events. But once you put in some disorder, once you put in some microcracks, you just get the pure power law emerging, even very near the failure time. Again, it starts off with this exponential nucleation dominated. Then you get growth and coalescence dominated. Long ago, Patience-Cowie showed this as an emergent property in numerical models for fault populations. And this is also what you see in the field when you measure them, if you have enough bandwidth. The correlation dimension is defined by the slope of the probability distribution of intercrack spacings. And we see another nice fractal emerging in a finite bandwidth. This is not a correlation length. This is just the effect of the finite size of the sample. Correlation length is way beyond this. So now we're looking at changes in crack shape. What we find is that the crack aperture, you maybe saw that from the images, but the crack aperture is not very variable. So we're getting cracks which are pretty much the same width, the same opening. Sorry, the same aperture. The width increases with time. It doesn't change very much in the initial loading phase, but once you start to get yield, you see the width increasing, and the length even more. So, and that's the same in the heat-treated sample. Maybe it's a little bit more reactive in parts. What this is showing is that the crack growth is not self-similar. So we've got self-similarity in the size distribution and the correlation of where the cracks are, but the aspect ratio is not self-similar, it's self-affine. So as it grows, the aperture is not really changing. So the cracks are becoming longer, they're becoming wider, but they're not thicker. And that means that this will give us some clues as to how to interpret changes in seismic anisotropy in experiments like this. So now I'm going to look at sound and vision. Thanks to David Bowie here, I've copied his title for the album. Acoustic emissions, we're recording. We're going to observe the deformation directly in the rock. We're going to infer the strain field. This is, in this case, it's the incremental dilation in strain. Well, it's microstrain, isn't it? 2 to 10 microstrain units, which seems very small, but we can detect it in these small samples. And we're going to copy a protocol first used by Dave Lochner and his group at Menlo Park, published just over 30 years ago. Seminal piece of work, this, where they deliberately took the sample over peak stress and then back down the hysteresis curve to try and slow down the process of failure so they could see it on the timescales of a normal deformation experiment. So they could see the localization process. And using this feedback, they confirmed that the damage is distributed initially at point A, then it starts to localize, and then it grows to produce the fault. And so this has been the standard model for a long time now. The problem is, all of this, if you did a normal test at constant strain rate, all of that would happen in a fraction of the time of the test, maybe a fraction of a second even. So you cannot capture this behavior we see on the right with a standard test. You must put in this feedback control. So we copied this on our granite specimen. Here it is again. Notice it's got these phenocrysts that have decayed, but there's really very little structural disorder in this starting material. And then we're going to look at how this evolves in the synchrotron as we squash it up the stress-strain curve. And we start with observing randomly distributed microcracks, just like in Dave Lochner's experiment with the acoustic emissions. And then we use the feedback, and as we go up the curve, we begin to see clusters, little correlated. Often in the granite, it's vertical clusters, indicative of tensile microfracture. And then they start to grow. And this is consistent with our interpretation of the frequency size distribution of these objects. We've got random nucleation, and we've got growth and cluster and coalescence. And those are the features that give rise to the power law and the frequency size distribution. And then we get to peak stress. Bang! We can't see anything in this conventional test at constant loading rate. And then afterwards, we have a look at the sample after, and we've got the shear fault. And we've no idea where this came from. You could not have predicted this from that, even though you're looking at this system in this great detail. Okay? So prediction is really hard in complex systems, especially brittle complex systems. So how did this happen? So you cannot do this from a standard test where you just allow the sample to break at peak stress. So, as I say, we constructed a cell to repeat this protocol. So the sample goes in there. You can see where it is. And it goes in this confining pressure vessel. Okay. So one of the things you notice is that you can see the sample. Okay, we've made a cartoon, but you can actually see the jacket around the sample in this confining medium. But unfortunately, we cannot put transducers on the side of the sample. Why not? Yeah, it would obscure the X-ray. The X-rays are going to come in from the side, and then you're going to have the plate behind it. So you would scatter the energy off the transducer. So you can't have any transducers on the side. And what we've done is we've put them in the top and the bottom only at this stage. So we have the transducers in the hollow ram and piston. And at the moment, it's just a one-component sensor. And so this is the arrangement of the transducers in the sample in the cell. And then we can take wires out and we can sit and listen to the deformation. And this is the setup in the lab, ready to receive X-rays. Of course, you don't stay in the room when the X-rays are on. So here's two experiments. The red is the conventional 10 to the minus 5 per second strain rate. Goes over the peak stress, and it goes bang. And here's the one with Dave Lochner's protocol feeding back on the acoustic emission event rate that we record in these detectors. So in this case, we're using the sound to control the deformation. And then we do the X-ray scans at the dots. So each of these dots is a time when we do the CT volumes, image the CT volumes. And we find out that the optimal feedback rate was about 1 acoustic emission per second. So every 10 seconds or so, you'd have 10 events, and you'd either increase the stress or back it off, depending on what is needed to maintain the acoustic emission event rate constant. In fact, you cannot maintain it constant. Here's the test where we've got the number of acoustic emission event rate per second. We control it on 1, but there's a big dither on the feedback control, so it's constantly jumping up and down, a bit like a tennis player on the baseline, ready to go either way. So it isn't really stationary. There is a dynamic effect you can't help but introduce. Nevertheless, we were able to stabilize the deformation. Okay, so there's a peak stress, and there's a difference you can make if you feed back on the acoustic emission event rate. And yeah, we've reproduced the protocol from the Lochner et al. Experiments. Oh. Now this is, maybe it doesn't look it, but this is the highlight of the talk. This is a rock breaking in front of your eyes. Wow. We thought when we saw this, it's sort of virtually jumping up and down, except it takes so long to get this image from the experiments. Months later, you begin to see this. So much work. But look at it, it's doing a lot of the things we expect. It's initially, actually it's not shown here that well, but you see compactive stress, and you see damage in the sample. Then you see the localization. And what was surprising was the localization almost immediately on localization. The whole of the sample is covered by a shear band. See? So you don't really get nucleation of the shear band. That comes later. The first thing that happens is that these tensile cracks align across the sample virtually instantaneously. And this is what makes failure hard to predict. How would you know from the measurement immediately before that point that that was going to happen. It's really a very, very nonlinear process, the localization. Yeah, so I'm going to home in on some of the details now. Most of the deformation at peak stress comes around here, and then you get this localization associated with the strain softening phases. It goes beyond the peak stress. So I'm going to just run this movie now, one shot at a time. So this is just after we've started to get some tensile cracks, some damage, and it's kind of correlated on what is going to be the fault plane. So even at this stage, the fault plane it doesn't exist, but you could make a guess as to where it's going to occur from the correlation in the damage. And then you see the shear. So we're already getting coherent slip of the whole of this block, over the hanging wall, a structural geologist would call it, before there is a fault. So we have a shear band which is producing coherent motion of the upper block before there's a fault. And then we see more damage. We see rotation of some of the broken grains. Conventional transducers won't pick this up. So if you're looking for acoustic emissions from these rotating grains, you won't see it. And then in the extreme case, if you look here, you'll even see what a geologist would call antithetic shear. So if the grain rotates too much, it will then have shear in the opposite sense of the main fault, the main shear band. So I'll shout. The main shear band is going like this, and these grains are going the opposite sense because of over-rotation. So there's a lot of detail in the structure which we expected to see from these cartoons, and then there's a lot which the seismic inference was not able to detect in the observations. Okay, so we get these en echelon tensile cracks, and they develop very early to produce an aligned deformation band. And they also involve volumetric strain. So the shear is associated with a zone of dilation. All these tensile cracks. And the shear occurs by rotation, which is an aseismic process, sliding along some grain boundaries, which you can see in some of these images, including newly formed boundaries where you break the cohesion between the particles. Synthetic, and if over-rotated, we get antithetic sliding on the rotating cracks. And a very strong correlation, visually, you can see this, I'll show this later as well, between the dilatant and the shear strain. And then eventually, you get this coherent slip where the whole block is moving. And this is all before you eventually get a contiguous fault plane. So you have to distinguish between a shear band and a fault, where there's a contiguous connection between all of these features, where you can take a pencil and draw a line right between all of the connected elements of damage. Okay, so now we're going to look at the shear strain. So this is from particle tracking. And we start initially by, it's very difficult to see because it's totally distributed through the sample. We get randomly uniform compaction, which is sort of too small to see on this scale, actually. And that's associated with this material hardening in the early stage of the deformation. This is a sandstone sample, so it's relatively compliant compared to the granite test I showed earlier. And then we get this phase, long phase of what looks like elastic behavior So we know this is not elastic because it's nonlinear and because it's associated with compaction, random uniform compaction. And then at peak stress, it's difficult to see, but it's this middle stress, if you like. I don't know if you can make out. You're starting to see some purple, so these cool colors. Even when this is linear. So linear stress-strain relation does not mean there's no damage happening. The damage is happening. It's very small amplitude. And this is the shear strain. But can you see that? It's not very convincing, but it is there. Our interpretation of this linear phase is that it's predominantly elastic, but there is a compensated phase of damage and healing occurring all through this phase. So there's a balance, there's a dynamic balance of a small nonlinear component associated with compaction and maybe some incipient microcracking. And then that becomes more obvious. Once you get to yield, you start to see more obvious damage. Quite often this occurs in the test. The damage nucleates preferentially from the base of the sample, which is not moving. These are 3 different snapshots on the top. It's difficult to get rid of these edge effects in a laboratory test because of the difference in material properties between the RAM confining medium and the rock. Once it gets going, you start to see maybe 2 candidate fault zones. And as you go over peak stress, now we've kicked in the acoustic emission feedback, we see a relaxation. So you drop the stress, you see a relaxation. Less strain in that increment than you would expect if you carried on loading. So like an elastic rebound kind of thing. But then you start to see the nucleation of the high strain element of the shear band. So the whole shear band exists at this point, but we start to see this concentration of deformation on this nucleating sort of zone of high deformation. And then that grows right through this phase of strain softening. And you get to a position where you've got the maximum strain rate occurring at this kind of inflection point almost. High, strong colors, hot colors, as you start to go over the middle of this kind of phase. And at this point, you've almost broken the sample with high strain. And then once the fault exists, once you've actually got frictional sliding in between these 2 images, then again, you see another relative relaxation of the strain rate. So we see 2 relaxations, one just after peak stress, and one after the fault has been formed, when we can draw a line from one side of the sample to the other through contiguously broken elements. And look at that. Oh, oops. Yeah. So this is like collecting together, where these are occurring. And this is the feedback control, just to remind ourselves that we've slowed down the deformation to be able to see any of this at all. Normally this would happen too quickly to image. And there you go. So I don't need to say anything. So Dave Lochner and his group were right. This is where the deformation is occurring, and it's growing like this, but it's a bit more complicated than that, especially in the lead up to this phase. And then, because we've got the strain fields now, we can look at compaction, dilatancy, shear strain separately. Shear strain in blue, the dilation in orange. Yellow is compaction. Compaction is happening all the time. Even when the fault is forming, when the shear band is forming. So you still have compaction. So we don't have one process, then another, then another. They're all occurring all the time, just in different proportions. And these are the different stages, the initial loading, yield is phase 2. And then we have this phase of exploratory strain localization. I've not shown you the diagrams for this, but the first sort of correlated structure isn't necessarily the one that eventually breaks the sample. Sometimes and in this test as well, the system explores a potential fault plane, and then it stops. For some reason, it's not optimal, and it switches to another one. So in this post-yield phase, you can have exploratory strain localization. This is blind exploration. This is the system looking for some minimum in the free energy. It's not a kind of controlled, intelligent search for it. It's a sort of simulated annealing approach. Sometimes the first exploration of correlated shear isn't the optimal one, and it switches off. And eventually you get shear band formation right across the sample at peak strain. And that's associated with a peak in the damage, even the compactive damage. And then we got stable sliding on a newly created fault. And this is where the real friction is now coming into play. Up to this point, it's not obvious that friction is a major control. It's mostly the tensile fracture and the breaking of bonds between the grains, in the breaking of cohesion. Now, from the, oops, this is interesting. Why is that happening? It wants me to say I've got it. Okay. It's trying to teach me how to. Okay. Now we're going to look at the orientations of the fractures, and oops. The main one, most of the fractures are actually compaction, by number, maybe not by deformation or anything, but by number. Compaction, tensile, 90 degrees, dip, and then the two conjugate shear directions, and they're equally likely. You know, the reason the fault chooses this orientation and not that orientation is some random little kind of decision the system makes as to the optimal path to release the energy. We also see evidence of little secondary peaks at the Riedel shear direction. Maybe one of these on their own would be not very compelling, but the fact that they're all there it provides evidence that maybe there's some secondary Riedel shears occurring as well. So this shows that the dominant fracture orientation, 90 degrees and 45 degrees, dip in either direction. Those are the directions where, if you've got a granular medium, the only thing that's controlling shear is the cohesion of the material, not the friction. Okay? So how is it that these elementary cracks at optimally oriented angles to avoid friction eventually produce a 60-degree oriented fault? So we think it's something to do with the packing of the material. If you force the system to have only tensile and only shear at 45 degrees, then the net angle that makes in a cubic close packing is 60 degrees in an ideal sort of lattice. Okay, so maybe the origin of macroscopic friction, 60 degrees is the angle that you see in normal faults for, you know, sort of crustal scale faults. And it's probably controlled by the grain scale. That emergent angle is probably controlled by the grain scale, which Roberto Rizzo also suggested independently. Why is it doing this? Maybe you just need to ignore it. So basically, we've got a stairway of these wing cracks. Damage mechanics modelers would call these wing cracks. So it's a bit like a step, except that imagine walking up a step at 45 degrees. It's a bit like the dune the other day. And so we've got this staircase of wing cracks that's making up the friction angle of on the order of 60-degree dip. So if your idea of heaven is frictional slip, then maybe this is the stairway to heaven. This is Led Zeppelin's album cover. So the thing is, only cohesion is important. It's just the breaking of the bonds that's important. If you don't have this configuration, but locally you have grains on top of each other in a column, then the mechanism of tension is Hertzian contact. It's not actually this bond-breaking effect. So this isn't the whole story, but it gives a sort of toy model as to how this might come about. So the acoustic emissions, I mentioned the Pareto distribution, and that's what we see. That's the number of events as a function of magnitude. See a nice power law. It's a very high exponent, possibly because we have such a strong feedback control. The downside of working in a synchrotron is it's incredibly noisy. So we have a very narrow bandwidth. And that also might lead to the p-value being a bit too high. But what it means is that the deformation is dominated by the smaller events. So it's the opposite of the Pareto distribution for normal seismicity, where the biggest events dominate the energy release, or the release of seismic moment. So here they are. Here's the acoustic emission amplitude. You've got some sort of detection threshold here, and then you've got the events. And remember, we're purposely making this a quasi-stationary process. So you see there's not much variation here. There are fluctuations because of the dither on the feedback control, which are bigger than Poisson. Even though you've got few events, that's still a bit bigger than Poisson. Okay, and then the interesting thing is that if we compare what we get in the dynamic loading, obviously it's all over much more quickly, and we get this inverse power law acceleration. For the sandstone, we can nicely predict the failure time from these data. So if you've got a heterogeneous material, high porosity, it's easy to predict the failure time exactly, more or less. Plus or minus the uncertainty of the model fit. There's no real failure time here. It's a quasi-static failure really drawn out. So here's a constant event rate. But what this has done, by feeding back on the event rate, we've stopped the big events. Okay? We got better at adjusting the gains. This is the second experiment we did, so we got better at adjusting the gains, and we've got a broader bandwidth of acoustic emission event sizes. We detect more smaller events with the preamp set at the right gain. It's difficult to know until you actually get to the synchrotron what the optimal settings are. But we have reduced the number of big events by feeding back on the event rate. Now, this is interesting because the most legislative efforts to control induced seismicity rely on feedback on the maximum magnitude. Okay? So in Britain, we can't make more than a magnitude 1 without stopping experiments to do hydrofracture, for example. But that's not actually necessarily the best way of controlling the maximum magnitude. It's maybe better to control it on the event rate. And this was done in mining settings. Peter Stiles and others devised a system for monitoring mines. And when there was 100 events a day or some some rule of thumb, they would evacuate the mine for a day. And then the miners would go back in if the seismicity had died down. So there's an example of a transient response that was long ago operationalized. They basically waited for the seismicity to calm down, and then they went back in again. But he did it on the event rate. So maybe the event rate is the best way to control the risk in subsurface engineering applications. Location of the events is a challenge. We've only got 2 transducers, but we do have the strain. So we've got this kind of, for any pair of arrival times, we've got these different possibilities of where the event might be on this kind of manifold, sort of a bowl shape. But we've got the strain increment. This is the difference between 2 time snapshots. And then we can take the intersection of this manifold with the most likely source of this is where the high strain is. And so we adopt that as the best estimate. Essentially, we're using the strain map as a Bayesian prior on the acoustic emission location. And then this is what we see. This is maybe not that distinct. Here's an event. There are not many events. Here's an event in the sandstone. It doesn't produce as much as the granite. We see events that are on the fault plane, events that are off it. We see there's more than one attempt to localize the deformation. And sometimes acoustic emissions are associated with that. Sometimes they're just in the host medium. And then we can see some, clustered along the incipient fault plane. This is the shear strain, or formally it's the deviatoric strain on the top, and the dilational, the volumetric strain on the bottom. And you can see how strongly correlated these two are, just like we expected from looking at the raw images. So the problem with the CT is you've got to have a small sample. That means a small volume. That means not so many acoustic emissions. So we're hoping to go to a bigger sample in the next generation of tests. But what we do see is that there's a very strong, these are all of the acoustic emission events, all of the strain events. This is the deviatoric against incremental volumetric strain. And the acoustic emissions are preferentially picking, in the color here, the acoustic emission amplitude, we're preferentially picking zones where the dilational and the volumetric strain are correlated. So there's a strong correlation between volumetric and deviatoric strain, but there's an even stronger correlation with the acoustic emissions preferentially picking source locations where that is strongest. So only a small fraction of acoustic emissions, this is because we've got a very small number of them, occur in locations where the strain is recorded. There's a strong correlation between tensile and shear strain for events with an acoustic emission location. There's minimal acoustic emission for compaction, which is a pity, but you can imagine why that might be the case. It's more of a quasi-static process. Unless you've got very porous material and you see sort of bridge collapse and features like that. There's no strong correlation between acoustic emission amplitude and local strain. And together, these confirm that the strain is predominantly aseismic. So there's a lot going on that we're not recording with acoustic emissions. And that's maybe something to bear in mind when we're looking at the Earth too. In some tectonic settings, all the strain is seismic, and in others, in engineering applications, it's really, very often it's not. And this partition between seismic and aseismic strain is one of the biggest unsolved problems, I think, in seismology just now. So this is our surprising result, where the strain amplitude is high. Even though we forced it to pick the biggest strain location we still see that they tend to be lower strain. So a lot of the biggest events are happening in the intact rock outside the shear band. And that's because we think there are many aseismic mechanisms of shear within the shear band, the rotation of the grains that we wouldn't pick up with the seismometers and so on. This is not entirely a surprise because in material science, people have been looking at this as well in terms of avalanche dynamics. And there's a good fiber bundle model which also has this property. So it's not entirely unexpected in terms of physics. It was a surprise to us because we weren't thinking we would see this. But it was, if you like, predicted by this fiber bundle model. So we'll go to the conclusion. We see emergent power laws very robustly. And they occur in the evolution of the damage, in the number, the volume of the crack population, the frequency volume, the frequency spacing distributions, just like we see for earthquakes. Cracks go longer and wider, not fatter, and that will change the anisotropy in the medium by changing the aspect ratio. So if you assume the aspect ratio is constant during a deformation test, then you will get a wrong interpretation of the seismic anisotropy. The weakening, the strain softening occurs by self-organized localization of deformation on a shear band, and that happens very early after peak stress. Even before you get this apparent nucleating zone of acoustic emissions, as in David Lochner's experiment. It's just that that's picking up the maximum strain above some threshold. The whole thing is already organized, ready to go. And that's a bit of the magic of the emergence of faults in brittle materials. It happens very quickly. So the image, the knowledge that this bit is broken has gone to the end of the sample very soon after peak stress, through the stress interaction between the elements. Even though there's not a fault there, the knowledge has been transferred very quickly. And what we've found, I haven't shown too much evidence of this, but the system kind of explores many possibilities. I think I did in some of the slides, before it picks the optimal fault plane, and that's round about a 60-degree dip, which implies an internal friction coefficient of about 0.7, which almost every material has, apart from Teflon and a few others. And then this plane is a staircase of the wing cracks. It's made of tensile and shear elements by a mechanism which, or it could be, by a mechanism which has minimum work. It's not doing work against friction, just against cohesion. There's an intrinsic correlation between shear and dilational strain. And there's a large fraction of aseismic deformation in the shear band. And the biggest events actually occur off the shear band in areas of low strain where it's still brittle. It's not so granular, if you like. It's not so cohesionless. And then we found that large magnitude events, this was not an intention to discover this, but this is something we discovered because mostly we were interested in the structure. But we find that the large magnitude events can be suppressed by the feedback control on the acoustic emission event rate, and maybe this is a good thing to think about in terms of risk management for induced seismicity. And then I'll just leave you with this slide, which is a picture of Perthshire. You can think about this for next year. We may not stay in this castle, but we'll be somewhere nice. Thank you.